So based off our discussion of natural variable relationships, we get to talk about fugacity now. And fugacity is a pretty complicated idea, and we're going to try to simplify it down. We're not going to do a ton of math associated with fugacity, but you have to know about its existence because it's really going to help us understand equilibrium in a much more deep level than what we saw in general chemistry. I have the definition of fugacity written down here. It's the effective pressure of a real gas. What does that even mean, effective pressure? Well, we're going to talk about that in a second. Okay. Another way to think about a fugacity that's also a confusing way to think about it, especially with what we've talked about so far. But this definition will make more sense when we get to equilibrium. Fugacity is the activity of a real gas, right? So what is effective pressure? What is activity? What does that even mean? Again, these are concepts that we reinforce as we go through the semester and we look to actually get into equilibrium as a whole. But for now, what you need to know is that activity and effective pressure, they both mean the same thing. They both mean that fugacity is literally a mathematical construct to keep mathematical forms consistent with standards. All right. Fugacity is a mathematical construct, all right, used to keep the forms that we see in the mathematics, all right, consistent with standards. And when we talk about standards, we talk about ideal situations, right? And that's where the idea of effective pressure comes from. What we're going to see even today is what we'll have as a standard that we'll be discussing. That's an ideal gas standard. So in that ideal gas standard, P comes out as a natural variable, just pressure, right? Now some math will change, right, for real gases, but we want to keep the mathematical forms the same, right? It's all about keeping these mathematical forms the same. So what we do is we literally define something called activity for other situations, but we're going to call it fugacity for gases. We literally define something that keeps the math looking the same, keeps the math consistent, even though it's essentially not directly the pressure, it stands in for pressure for real systems. Anything that we can do ideally with pressure, we can do with fugacity for real systems. So again, it is a little bit of a complicated process and a complicated idea, but we're going to try to drive the idea home by looking at a simple example that starts with a natural variable relationship that hopefully you just were able to derive yourself. So our discussion of fugacity starts with partial G, partial P at a constant T being equal to the volume. So in your derivation of the natural variables of G, this was a definition that came about in that process, okay? So we know that we can rearrange the differential equation. I can write this as a dg equal to v dp, and then this is valid for isothermal processes. And we should be familiar with how to do this. I'm going to integrate both sides between two different pressures. On this side, instead of writing a delta G, I'm going to show that we change the pressure by writing G of P2 at R, isothermal temperature, minus G of P1 at R, isothermal temperature. So normally in the semester, we call this a delta G. Now for reasons that you'll see as we go through, I'm not going to write it as a delta G. I'm literally going to show the two G's that are being subtracted inside the delta. And remember, we're integrating over pressure, okay? So the two G's differ in terms of their pressure. They have the same temperature because everything is isothermal. Over here, this is integral P1, P2 of V dP. Now, what we're going to do is we're going to apply a standard to this. So this is a general definition for any gas. Now, what we need to know is how V changes as pressure changes, substitute it in there and integrate, okay? But that can get pretty complicated. So let's define a standard that utilizes an ideal gas. Now, doing so, we know that V is nRT over P, And we can do this substitution in there, right? We can throw that in there and we can get an integral that we're really familiar with. The nRT will be brought out front. We'll have dp over p. We can integrate that to get a natural log. So as we do this integration for an ideal gas, now we use this keyword ideal gas, right? What we'll have out of this is nRT, the natural log of P2 over P1. Now, when we talk about applying standards later on, all right, we like to pick, all right, what this P1 is. And we like to say, okay, our standard is not only just some random pressure, our standard is an ideal gas with a P1 equal to 1 bar. So let's set that up. Oh, we know that we would call that P naught, where the naught stands for a standard situation. So then finally what we can do in our expression is this P1 doesn't stay as a P1, it becomes a P naught, right? And this G, because it's at the standard pressure now, becomes a G naught. And what we do is, and you can rewrite this step in your notes and I'll give you a second to do so. We don't even write the P dependence in there because if I put a naught up here, I'm already telling you that that's the G evaluated at 1 bar, okay? So with this natural variable relationship, we end up with this very important and useful way of talking about how G changes with pressure. So if I change pressure, G changes as well. I can look at a table. I can figure out what a standard G is for that table temperature, okay? If I want to take from 1 bar and change the system to like 2 bar or 3 bar or any other pressure, G will change as well. And this equation will tell you how it'll change. You get your table value for G, right? I look at nRT, P2, throw it in there and analyze it, and I can solve for this G, right? Now on our table, what we normally get is a delta G, right? But imagine we had G's in a table, it would be the same idea, okay? This mathematical form is actually incredibly useful, and we like it so much in equilibrium that we say, okay, well, remember these steps where we assumed ideal gas behavior? What happens if we don't have an ideal gas? Well, then we won't get this simple form. All right, but we really like this form a lot. So imagine we invented this thing mathematically, where as we did that work, all right, we said, hey, we're applying the same standard, all right? We're analyzing the integral, though, in a different way. And as we analyze the integral in that different way, we're not going to get a nice simple form here, but we like this form so much that we group everything that we do find in that integral up into something that we're going to call fugacity. And this F right here, that's fugacity. To remind ourselves that this is the G for real gas, I'm going to put a little R here. And this is G for an ideal gas, I'm going to put an I there. Now notice, for any sort of real gas, the math is completely different, but imagine you could take all that stuff and keep the same form. Take all the things that you get out of that integral that was really nice for us and give us the natural log of P2 over P naught, right? Take all of that and just call whatever you get the fugacity and group it up into this form. That's what fugacity is. So now we can see how fugacity is an effective pressure, okay? So for real systems, fugacity is the stand-in for pressure. It keeps the mathematical form consistent, and it allows us to have this nRT natural log of something over something naught on the right-hand side, okay? The standard is the standard, okay? So no matter what, this is an ideal gas standard. Oh, so that means that this F naught and P naught, these are related as well. And if this standard is the standard, then you get this important relationship that P naught is equal to F naught, okay? So really the main difference between these two situations, where you have an ideal gas at a certain pressure and a real gas at a certain pressure, the main difference is fugacity is referring to the effective pressure of the real system, and pressure is pressure for the ideal system. To drive that point home, we can take these two expressions and we can subtract them. And it's interesting when we subtract these two expressions from one another, minus, plus, minus. We see that the standards go away. I'm going to have a GR of P2 and T here minus a GI of P2 and T here. On this side, I'm going to have an nRT, and I'll have two natural log terms that are subtracting each other. So I'm going to have the natural log of F P naught over P F naught using our natural log rules with subtraction. So fill in the blanks there if you have to. I'm going to use that P naught and F naught are equal to each other, and I'm going to cancel those out there. And what I'm left with is this incredibly important expression that tells us if I'm looking at an ideal gas, right, and I want an equivalent real gas for comparison, and I'm looking at the Gibbs energy, the difference between the Gibbs energies is equal to nRT and a ratio of F over P, right? So if I can figure out what the fugacity is for my real gas, and I look at the pressure of the system, I can compare the real gas behavior to the ideal gas behavior. And that's what fugacity is. Fugacity is accounting for realness. It's a stand-in for pressure that actually lets you mathematically account for real gas behavior. Okay? So because this is such an important idea, and it kind of sounds familiar, it's something that we can look at that actually deals with deviations from ideality, right? What we do is we look at this ratio here and we notice, oh yeah, wait a second, if this side equals zero, that means that my real and ideal difference in G is also equal to zero. That means I have a real situation. That means GR is equal to GI, right? And I have an ideal situation, sorry. That means that my gas is behaving ideally, okay? So we define gamma as F over P, and we say that this is the fugacity coefficient. Now this is going to sound familiar because it's really making measurements of objects or for situations that we discussed earlier, but it's doing so in a different way, because if you look at this, how does this disappear? The only way this disappears is if F equals P, and if F equals P, gamma equals 1. And if this disappears and I have a 0 here, that means what we have is an ideal gas. We have an ideal gas behavior because the fugacity isn't anything more than the pressure. There are no deviations from ideality. This sounds a lot like Z. You remember Z from earlier in the semester? When Z was equal to 1, we had an ideal gas, right? Now, gamma and Z are not the same. They're measuring something different, okay? But realizing that that convention that we established earlier applies here. When Z equals 1, we knew we had an ideal gas. Well, when gamma equals 1, we have an ideal gas as well. And again, just to make sure you understand, right? F over P, if I take the natural log of 1, I get 0. And then that means that these two guys are equal to each other. So that means that my ideal situation is my real situation, or my gas is simply ideal, right? Now, any deviations, right, the right-hand side of the equation, if gamma is not equal to 1, then what we're going to have is a real gas, and those two terms that we were subtracting aren't going to give 0, and we have real behavior. And remember, we saw this for Z as well. When Z was not equal to 1, we also saw that we have real gas behavior. So fugacity takes into account real gas behavior while keeping the mathematical forms of G consistent, okay? So that is why we call it an effective pressure, because it fits in the same spots that pressure does, but it does so for a real system, right? The fugacity and the fugacity coefficient, even more directly, is a measure of deviations from ideality, okay? Fugacity counts for real gas behavior, but when it looks like pressure exactly, then what we have is a gamma is 1, and we have an ideal gas. When fugacity and pressure differ greatly, that means that we have a situation where those real effects are important. Gamma is not equal to 1, and we have a real gas. There's a lot of complicated mathematics associated with calculating fugacities and looking at their functional forms, but we're going to have to skip over that due to the constraints of this semester. But you do have to know what fugacity is. It's a stand-in for pressure that we'll use for real systems, for deviations from our standard conditions. Okay? So try to digest as much as you can. There's reading assignments in your book that deal with fugacity. Make sure you chronicle any questions that you have and send them off to me, and I'll help you understand this difficult process and difficult idea.